Hello everyone, welcome to the course on measurement and instrumentation, and this is the second module of this course where we are talking about analog meters, and this is the 10th lecture in this module. So, we have already discussed about some of the meters like current measurement tool which is called ammeter, the voltmeters, and we have also seen in very brief about ohm meter. Okay, we have seen there are two different type of ohm meter and how their reading scale varies. Okay, of course we will be discussing them in more detail later. Okay, so let us learn about another kind of meter which is a galvanometer. Galvanometer is an instrument which is used for detecting the presence of small current or small voltage in a circuit for the measurement of their magnitude. Okay. A galvanometer is mainly used as a null detector and not for measuring large current. For example, in case of say bridges, for example in the Wheatstone bridge, this is very significant, where in place of say this is Wheatstone bridge, in place of finding current flowing in resistor R1 or in R2, R3 or R4, we are more interested in finding the balance condition where this ammeter or say this meter basically shows a null deflection. Okay. So, we say that in the balance condition there is null deflection. Okay. So, similarly, it is helpful in DC potentiometer circuits where it is again used as a null detector to obtain accurate voltage measurements. Okay. So, potentiometer we will see later on, and we will see that a meter is used there where that meter will say that okay, at this particular point the branch resistance or the branch potential is equal to what potential is being applied, and at that particular point this meter shows null deflection, and this meter is basically their de-Arsenable kind of galvanometer. Okay. So, let us try to see how these galvanometers are made up and what is the construction of this galvanometer. Okay. So, there are 5 important parts of a galvanometer. One is this moving coil. Okay, that you can see that this is a moving coil. This is a top view and this is a kind of side view of this galvanometer. Okay. So, this is one view, I am calling it say 1 and I am calling this 2. Okay. Fine. So, you have a moving coil. So, this is the moving coil I am talking about. Okay. You have a damping system. There is suspension system where you have upper suspension and lower suspension. We have already discussed about the suspension system. This is exactly the suspension system that we have talked about. Okay. Then you have indicating tool. This pointer is basically acting as an indicating tool, which is also, if you see this better view, you have a mirror system arranged. We will see what it is, and then you have a 0 setting. Okay. Let us see all of these one by one. Okay. Say let us talk about a moving coil. So, it is the current carrying part which produces deflection due to interaction with the magnetic field. So, this coil is placed on a former, this part is former, and inside you have core which is stationary. This is the former. Okay. So, this coil is wrapped on top of this former and inside you have iron core. Okay. Now, this moving coil is basically placed in this permanent magnet, and this is, although here it is looking like block of iron, but it is so this is basically a U-shaped magnet we have already seen. So, this U-shaped is coming from this. Okay. Basically this is coming from this U-shaped. Okay. So, this coil is placed. This is basically the current carrying part of the galvanometer which produces deflection due to interaction with the magnetic field. Okay. This can be rectangular or circular in shape and consist of number of turns of thin wires. Okay. This number of turns is very important, and we will see this in the mathematical equation of the deflecting torque also. Okay. So, the moving coil is suspended in such a way that it is free to rotate about its vertical axis of symmetry. Okay. Now, the coil is placed in a uniform radial magnetic field which is produced by this permanent magnet and a soft iron core. Okay. So, the field has to be radial, and this is a very much important requirement for this galvanometer system. Okay. And that is why the iron core's shapes usually is tuned as per the requirement. Okay. So, when the moving coil is circular, the soft iron core is spherical in shape, which then if it is spherical, then it will be able to produce a radial magnetic field. Now, when the moving coil is rectangular, as you have seen just now, core is now cylindrical in shape, so that again the field remains radial. Okay. The soft iron core basically provides a low reluctance path for the magnetic flux due to its very high magnetic permeability, because this is basically a soft iron material. Okay. Soft iron we have already discussed what is a soft iron or what is a hard iron in previous lectures. So, this core basically it concentrates and strengthens the magnetic field which ensure a uniform radial field and improves the galvanometer's sensitivity. Okay. When a current carrying coil like this galvanometer is placed in a magnetic field, the magnetic field again is produced by this permanent magnet. Of course, it will experience a torque, which is nothing but a twisting force which causes this coil to be rotated. Okay. Now, when it is rotated, this rotation of this coil, or you can see this in better way here in this configuration. Okay. If you replace this magnet with some stronger magnet or even stronger magnet, the torque produced will be even higher. Okay. Now, there is certain gap between this coil and this magnet. Okay. This gap I am talking about. Okay. This is called say air gap. Okay. So, this air gap is between this curved poles of this permanent magnet and the soft iron core. Okay. When this gap is very small, it produces a controlled magnetic field distribution. Okay. What it means that if you have say I am trying to draw say a curved magnet. Okay. Now, you have a say core which is at a distance of say 1 centimeter or say 10 centimeter. Now, you have this field passing through it, okay, or this magnetic field of lines, okay, and it is interacting with this core. Okay. The role of this core here is to make it radial. Okay. When you have this air gap too large, you will not be able to control the field distribution. Okay. So, to have better control, this gap is kept as small as possible, and usually since you have to also keep provision for this coil to be rotated, okay, this gap has to be little I mean there should be a trade off between, you know, say if this coil is hitting this magnet, or it should just pass from near to this magnet. Okay. So, there is certain optimization, and by this trade off this gap is kept around say 1.5 mm or so. Okay. Now, this air gap allows this magnetic flux to partially pass through it rather than through the iron core. Okay. Now, this introduction of this air gap increases the reluctance of the magnetic field, because this itself carries a certain amount of reluctance, okay, which is even much higher as compared to the material. Okay. So, this air gap increases the reluctance, which is basically the resistance to the magnetic flux of the magnetic field. Okay. So, the higher reluctance enhances the sensitivity of the galvanometer, making it very much responsive to even small current flows. Okay. Some galvanometer, particularly in the modern days, do not have iron cores. Okay. So, when you omit the iron core, reduces the magnetic flux density definitely. Okay. Now, because of this, when you have say I am drawing it once more, so that you have a feel that there is no core right now. Okay. You have simply, for example, a coil. Coil is in this case is looking like this, which is wrapped on a former. Okay. Now, when you do not have an iron core, okay, the coil is made much narrower to compensate the lack of the core. Okay. A narrower coil, when you have this narrow coil, it actually helps reducing the effect of air gap in the magnetic circuit. Okay. However, this kind of galvanometer is not that sensitive as compared to the iron core kind of instrument, and the galvanometer's coil in this case has smaller radius, as I have just mentioned. Okay. So, smaller coil radius reduces the galvanometer's moment of inertia as compared to the larger coils. Okay. When you have reduced moment of inertia, basically you have faster response even for a shorter current or even in a short periodic time. Okay. Although, as I have mentioned, it is not that helpful, but removing this, but it makes the device less bulky. Okay. And even the cost associated get decreased. Okay. So, this is about the moving part. Okay. However, I have just mentioned that along with the moving part, you have other parts also, like you have to have damping system. Okay. You should have controlling system, etc. Okay. So there is a damping torque present owing to the production of eddy current in the metal former on which the coil is mounted. So former itself is helping in inducing certain kind of eddy current which opposes any kind of oscillation. Okay. Damping in the modern days can also be obtained by connecting a low resistance across the galvanometer terminals. Okay. Damping torque depends upon the resistance, and we can obtain a critical damping by adjusting the value of these resistance that we have just connected. Okay. Then we have suspension system. So the coil is supported by a flat ribbon suspension which also carries current to the coil, as we have seen earlier also. This is called lower suspension and basically has negligible torque effect. However, this type of galvanometer has to be leveled. We have seen this as one of the disadvantages for this kind of suspension. Okay. So because they has to be vertically placed. Okay. So the galvanometer has to be leveled carefully so that the coil hangs straight and centrally without rubbing the poles of the soft iron cylinder. Okay. For indication, a small mirror is mounted on the suspension which reflects a beam of light. Okay. So the deflection of the suspension is measured by observing the movement of the reflected beam on a scale. Okay. Now zero setting is provided by a torsion head which is used to adjust the position of the moving coil so that it remains properly aligned between the magnetic poles, which this torsion head is small screw kind of thing which is of course movable in nature. Okay. This torsion head also helps in zero setting of the galvanometer by adjusting the restoring torques when there is no current flowing in the galvanometer. Okay. Now we have understand the basic construction, which is of course very similar to what we have seen in the electromechanical indicating instruments. Okay. Now let us try to understand the torque equation of this galvanometer. Okay. So to understand this torque equation, let us see that what is the force on each side of the coil. Okay. So if I say the force is directly proportional to the current which is flowing in the coil. Okay. And also it is proportional to the flux. Okay. Or I say it as B. Okay. Now we have already seen that this force is equal to this current. So you have multiple coiling is something like this, right. So you have to also take into consideration the number of turns. Okay. So this force is equal to say N B, say N I into B, or say N B I, okay, into length of the vertical side of the coil. So this is the vertical side of the coil, okay, because it is experiencing the magnetic line of force. Okay. So into L into of course sin alpha, which is alpha is the angle between the direction of the field and the conductor. So I am considering this each turn as a conductor. Okay. So the angle between this flux and the conductor is defined by this alpha. So the force on each side of the coil is given as NBIL into sine of alpha term, where alpha is the angle between the direction of the magnetic field and the conductor, and L we have just seen is the length of the vertical side of the coil, N is the number of turns of the coil, B is the flux density in the air gap in say Weber per meter square, and I is the current through the moving coil. Okay. So, this is say first equation. Okay. So, we have seen that force is equal to NBI into L into sine alpha. Okay. Now, we have done lot of iteration, like when you have this say circular turns of this coil, we have taken a spherical core, say rectangular kind of coils we have taken already, a cylindrical kind of core. Okay. We have done all the things to make the magnetic field radial. Okay. And when you have this radial field, this alpha will be 90 irrespective of the coil turn. Okay. So, when you have this alpha as 90, the sine alpha terms become 1. Okay. And the force becomes force on each side of the coil becomes NBI into L. Okay. So, this force is now NBI into L, and this is say for my second equation. All right. Now, we are not dealing in terms of force, we have to deal it in terms of basically the deflecting torque. Okay. To find the deflecting torque, we have to multiply this force with distance, and the distance is nothing but the length of the horizontal side of the or the width of the coil, and this is basically the width of the coil I am talking about. Okay. So, the deflecting torque is equal to force into distance, and force from equation 2 is given as NBIL, and this torque is given as NBIL into D value. All right. So, say I am calling this say third equation. Okay. Now, this L multiplied by this D value, okay, the width of the coil, okay, it is basically it define the area of the coil. Okay. So, by replacing this TD, so this is I. Okay. So, this TD is equal to NBA into I, where A is the I am calling this say equation 4, where I is the current which is flowing, and L into D is A is the area of the coil. Okay. And if you see N, B and A, N was the number of turn which is fixed for a galvanometer. Okay. You are not changing the coil every day. This is the magnetic flux. Okay. This is also constant. Okay. And this area is also constant. Okay. So, TD equal to certain constant into the current value. Okay. This equation 4 now written as TD equal to G into I, where this G is equal to certain constant which is NBA, where A is L into D, and I am calling this equation 5, and this is the deflecting torque acting on the coil. Okay, or this is the deflecting torque in the system. Okay. This equation 5 is a very important equation in this galvanometer, and this is the foundation stone for the deflecting torque for other kind of system, like we will discuss in the PMMC or moving iron or other kind of systems. Okay. In this equation, this TD is equal to G into I, and in this equation this G is known as a displacement constant of the galvanometers. Now, we have this equation TD equal to G into I. Now, what we have to do is we have to also find the control torque or controlling torque, because at the steady state position we can equate them to find the deflection, because till now we have not deal with any kind of deflection. Okay. Now, we have the idea that what is the deflecting torque acting on the moving system, but yet we still have to deal with deflection. We have not encountered it yet. Okay. So, G is called the displacement constant of the galvanometer. So, TD is equal to G into I. Okay. The controlling torque exerted by the suspension at a deflection say theta f is given as TC is equal to K into theta f. Of course, this is coming from spring constant. So, K is the spring constant of the suspension, right. So, this is say equation 6. Okay. So, now equation 5 is the equation for the deflecting torque, and equation 6 is equation for the controlling torque, and theta f in this case is the final steady state deflection of the moving coil, of course in radian. Okay. So, we have a final steady state deflection at which this Tc will be equated to Td. Okay. So, if I equate Tc with Td, I have this k theta f equal to G into I, or the final steady state deflection theta f can be written as G into I divided by K. So, this is current. So, G into I by K, or the deflection is written as G by K into I. Okay. Now, this deflection is very clear to us, and I am calling this equation 7. Okay. Now, let us try to understand the indicating part in this case. Okay. So, if the deflection is measured say on a millimeter scale, which is placed at a distance of say a meter from the mirror, the deflection can be written as d is equal to radius into the angle which it has turned. Okay. So, this now this equation is true only when this theta f, this is theta f, when this theta f is very small. When this theta f is very large, this equation, the deflection equation may be wrong. Okay. Now, this is 1000 mm, I am considering it, we have already considered it to be at a distance of a meter. Okay. This is 1000 mm. Okay. This 1000 mm into the angle which it has turned, and this angle turned, in place of theta f I am writing 2 theta f. Okay. This 2 theta f is coming because if the deflection is say theta f, the mirror that you have seen turns through an angle theta f, while the reflected beam turns twice of that. Okay. So, the turn of this reflected beam is 2 theta f for a deflection of theta f, and that is why this turned angle is written as 2 theta f. So, the reflecting beam is 2000 into theta f, and theta f from equation 7 is given as G into I by K. So, this is what it indicates on a millimeter scale. All right, fine. So, we have now understood that how this moving system, control system, and indicating tool works in a galvanometer. However, till now we have mostly seen the steady state relationship. Now, let us try to see the dynamic behavior of a galvanometer. Okay. So, now when current is passed through a galvanometer, the pointer basically does not reach the steady state deflection instantly, and that is how we have been studying since class 1, lecture 1, that we have to have a certain provision for avoiding any kind of oscillation. Okay. So, there exists a finite time basically, which is the transition period during which the moving system respond to the applied current which it is measuring. Okay. So, during this transition period, the moving system deflects from its initial position to final steady state position, and the dynamic behavior of the galvanometer during the transition period is studied using the equation of motion. So, once we have the equation of motion for the galvanometer, it is a little bit easier to understand its dynamic behavior. Okay. So, with suitable modification of the constants, this equation of the motion is applicable to most electrical indicating and recording instruments, including the galvanometer. Okay. So, before we actually jump into the steady state or say this equation of motion for the galvanometer, let us try to understand some of the constants which is very relevant to galvanometer, which we have to recall maybe in the later lectures. Okay. So, let us try to find the some of the constants which relates to the galvanometer, and first and foremost is the intrinsic constant of the galvanometer, which we have recently seen. Okay. So, let us consider this constant of a galvanometer. This is basically the first intrinsic constant of a galvanometer is the displacement constant that we have just seen, and this comes from the deflecting torque equation, where we have seen that Td is equal to G into I, where G was equal to N B into A, where N was the number of turn, B was the flux, and this was the area of area. Okay. So this G is basically known as the displacement constant of the galvanometer and has a unit of, say, Newton meter per ampere. Okay. This is very important. The second intrinsic constant of a galvanometer is the inertia constant. Okay, or say sometime also called inertial constant. So the inertial constant of a galvanometer represents the effect of the moment of inertia of the moving system, which produces a retarding torque due to already present inertia. Okay. This inertial torque is proportional to the inertia constant and the angular acceleration of the moving system. Okay. So if I have to write mathematically, the inertial torque can be given as Ti equal to J into d2 theta by dt square, where this J is the moment of inertia, this J is the moment of inertia of the moving system about the axis of rotation. Theta is the deflection at any time t, and this of course t is the time, and theta is in terms of, say, the unit is radian, and this J value here in this case is called the inertia constant of the galvanometer. Alright. So these intrinsic constants we may have to recall at any time. Then third is the damping constant of a galvanometer. So damping in the case of galvanometer is provided by the friction due to motion of the coil in air, and also by the induced electric effect if a closed circuit is provided. So damping torque is assumed to be proportional to velocity of the moving system, and the damping torque equation can be written as Td equal to d into d theta by dt. Okay. And in this case, this d is the damping constant and has a unit of, say, Newton meter second per radian. Okay. So this is another constant of a galvanometer. Another constant of a galvanometer is a control constant. So a controlling torque in the case of galvanometer is produced due to elasticity of the system, which tries to restore the moving system back to its original position as like any other tool, and controlling torque again is provided by the spring and is given as Tc equal to k theta. K we have seen as a spring constant, but it is also known as the control constant in case of galvanometer. Alright. So once we have understood all these things, now it's very easy to understand the equation of motion of galvanometer. So what we have understood till now, that there are 4 torques acting on the moving system. Okay. The first torque, or only one torque, is trying to deflect the system or trying to accelerate the system, which is the deflecting torque Td, while other 3 torques, which is the inertia torque Tj, damping torque Td, and the control torque Tc, is trying to retard the system. Okay. So one torque is trying to accelerate it, and while the combination of other 3 torques is trying to slow it down, or it is trying to retard it. So for any deflection, say theta, at any instant of time, say t, this Td under the, say, quasi steady state condition, this Td, which is the deflecting torque, will be equal to Tj plus Td plus Dc, or the accelerating torque will be balanced by the other 3 torques, which is the inertial torque, damping torque, and the control torque, and this lays the foundation of this equation of motion. So if you equate this Td with the other 3, summation of the other 3, Tj, Td and Tc, you have this Gi is equal to, say, S theta plus or say k theta plus d theta by dt plus j d2 theta by dt square. Okay. And this will be, if you see, this is a second order equation, and you have a linear second order differential equation, and if you try to solve this, the solution is sum of a complementary function representing a transient condition and a particular integral representing the steady state condition, and based on the solution you can actually comment on the damping condition of the galvanometer. Okay. So we will of course not solve this equation of motion for the galvanometer, because because we have to study other kind of meters, but if you are interested, you may try to solve this equation, and based on the solution you can comment on the damping of the system, be it over damping, under damping or critically damped system. Okay, so all these things is coming from this equation of motion. Okay. Another important thing for this galvanometer is its sensitivity. So, we will try to understand the sensitivity of the galvanometer, and then we may complete this galvanometer topic. Okay. So, the sensitivity of a galvanometer can be defined as in terms of current sensitivity or in terms of say voltage sensitivity. So, when I say current sensitivity, the current sensitivity of a galvanometer is defined as deflection produced by a unit current. Okay, in the galvanometer. So, if I say current sensitivity, it is defined as the deflection divided by the current. Okay, or if I rephrase it, theta f we have already seen is equal to Gi by K, or Si is equal to Gi by K. So, this is the current sensitivity, and if in terms of voltage sensitivity, it is the deflection in scale division per unit voltage of the galvanometer, very similar to what we have seen for the current sensitivity. So, if SV is the scale division per unit voltage, basically you can calculate the voltage sensitivity of the galvanometer. Okay. So, this sensitivity of the galvanometer we may recall when we will talk about the resistance measurement using different bridge circuits, including a simple Kelvin double bridge circuit or any other kind of circuit. So, there these sensitivities, particularly when you deal with very low current or very low voltage, becomes very important. Okay. So, we will be trying to recall this voltage sensitivity and current sensitivity of the galvanometer later on in this course. Okay. So, with this we are finishing this galvanometer discussion. Of course, this is just an introduction to galvanometer. We will be again coming back to all the meters that we have seen till now. Okay. But in the next week, say which is week 4, basically we will start our discussion with all the analog meters, and in the discussion we will be taking the PMMC kind of analog instrument first. And if you have understood the galvanometer torque equation, it will be very easy for you to grasp the torque equation and other derived parameters for the PMMC tool, as well as for other kind of like moving iron or say dynamometer kind of tools. Thank you.